now we're going to look at a new type of function. So a function of several variables or of several input variables is a rule which takes the inputs, each input, by the way, is a real number, and specifies an output. That output will be a real number, a single real number. So we can describe this, first of all, by expression or formula. So for example, f of x comma y equals 2x plus y minus 4. To find f of 3 comma 4, this is not all that challenging. It's just follow the order of the coordinates here, plug in a 3 for x, plug in a 4 for y, so you have 2 times 3 plus this 4 is the y that we plugged in. Minus 4, that's just the minus 4 that was in this particular example already, so 6 plus 4 minus 4 equals 6. Another example using this function, f of 1 comma 10. So x is 1, y is 10. Just follow the order, right? X comma y, so 1 comma 10. So 2 times 1 plus 10 minus 4. We can also describe a function like this by a graph. Now, here's the thing. An input, it's really, an input consists of an x coordinate and a y coordinate. And then what you do is, so when you specify an x coordinate and a y coordinate, for example, x equals 1 and y equals 10, then you plug this all in and you get this output 8, and that's going to be our z coordinate. So that's why at the top where it says example, you have z equals f of x comma y. So you take the x comma y like 1 comma 10, and then you computed 8, and now that's the z coordinate, right? So this is a lot to take in, right? This is not easy to do. So let's click on this to see a picture. Okay, so this is a picture of the graph of the function. Let me scroll up here. Z equals f of x comma y equals 2x plus y minus 4. So at any specific, so you'll see here the x-axis in red, the y-axis in green, and then the z-axis in blue. And so at any specific input, so an input consists of an x-coordinate and a y-coordinate. So like let's just take, for example here, the x-coordinate 2 and the y-coordinate 1. So that right there, I'm trying to point to a point on the xy plane or the plane where z equals 0. So right on the floor. So that sort of location really just tells us input information. And then from that, x equals 2, y equals 1. Well, you can even look here right there and plug in. Let's just do this real quick. 2 times 2 plus 1. So 4 plus 1, 5. 5 minus 4 is 1. So we should get the output to be 1. And the picture of that, and it's hard to see this all, right, is that we're not talking about the point right down here that's in gray. There should be one and only one point that has x coordinate 2 and y coordinate 1 in the teal picture. And so from here we head directly up following parallel to the blue z-axis, and we get up here somewhere. Sorry, I'm not trying to point to the x-axis. Maybe I'll kind of rotate the picture here a little bit. So 2, 1. So if we, from here, from where my mouse cursor currently is, I'd like to try to head up in the sense of in the same direction that the blue z-axis is pointing. And if I do that, boom, somewhere roughly here, I'm trying to eyeball this, that would be the point on the teal plane. And it makes sense, by the way. We're really talking about this point on the plane should have z coordinate 1. It's really because what this is the graph of this function, but it really turns out to be 2x plus y minus z equals 4, right? Which we know from earlier is in fact a plane. Okay, so rearranging things. This is really 2x plus y minus z equals 4. It's a plane with normal vector 2, 1, negative 1. In this case, we just got really lucky because the formula for this function was real nice, right? But what's really happening here, just to bring it into function language, for each combination of x and y, we get one z value, the output. So just like our traditional functions from the past, the vertical line test passes, except our concept of vertical now is the z-axis is that vertical axis here. So the graph is three-dimensional, right? 2 dimensions for input. There's an x-axis and a y-axis because there's an x input and a y input. And there's one axis for output, and that's the z-coordinate here. So Yeah, two plus one, right? Two dimensions input, one dimensions of output. That leads to a three-dimensional graph overall. And we could do things like describe by table of values. So what I've tried to do here is like when you plug in x is one and you plug in y is two, you're supposed to get, if I did my arithmetic correctly, your z coordinate should be zero. Or so sort of all over inside the table are supposed to be the z coordinates. But this information is hard to depict very well in a table, and to be honest, that's probably the same when you just have a t-chart of x and y values. We'll come back to this function here, z equals, or f of x comma y equals 2x plus y minus z in a moment. But let's examine this tool here. We'll click on this, which is going to graph any function of two variables, x and y, for us. So let's click on this. Okay, so this one's going to be kind of messy, to be really honest, but what you're seeing the graph of is f of x comma y equals sine of x plus sine of y plus 0.01 times the quantity, absolute value of x plus absolute value of y. That quantity is squared. And it looks like this, right? So let's see. We've oriented now, so the x-axis is pointing towards the lower left, the y-axis is pointing towards the lower right, and the z-axis is pointing up. And I mean, it's kind of a funky looking thing, right? So you, there's a lot to take in geometrically. This is not something I'd expect you to draw by hand by any means, but let's just see if we can make sense of what's going on. First of all, sine of x plus sine of y. That part is really just trying to create a little bit of that ripple-like effect. And notice that what's happening to that is we're adding really this absolute value of x plus absolute value of y quantity squared. It's trying to create a bit of a parabola-like effect as you move around. And that 0.01 is just meant to create a vertical compression, because when I did this with just no number in front, which would effectively be a 1, it was just too tall to see what was going on. So you'll see that in this app, you can play with things, and you can kind of graph any function with two input variables to see what's going on. So for instance, if we take out that whole thing that was creating a bit of that add a parabola-like effect, sine of x plus sine of y kind of looks like an infinite, what would you call it, like the things that would hold eggs in bulk. Well, let's just see what it looks like. I should, maybe you have oh, what happened here? Let me erase this and then press enter. And yeah, here's what it is. That kind of visible? Maybe I'll use my scroll wheel to sort of zoom in. I don't know if this is going to work really well. Yeah, there we go. Right. So this is what it looks like zoomed in a little bit. Let me use my scroll wheel and zoom out, see more of it. So it looks kind of flatter because if you take a look, the z-axis goes from like a -20 to a +20. But I hope you can kind of see a bit of what it's trying to do. This periodicity in both x and y, meaning once you move plus 2 pi in the x direction, your picture should look the same all the time. When you move plus 2y in the y direction, your picture should also look the same. But then we could, I don't know, you can do all kinds of fun things here, like just adding a y squared alone would add the shape of a parabola as the points change. Well, let me correct the language. As you move from one point to a next, as long as when you compare one point to the next, all other things equal, let's say the x and z are equal, but the y coordinate, let me say it this way. If you keep the x coordinate, it doesn't even matter what happens with x, but as the y coordinate increases, you ought to see the z coordinate influence in the shape of a parabola. And I'm afraid this parabola is going to be too big. So let me again just vertically transform this by doing like a point, 0.5, like 0.3, something like that here. And so you'll see now the effect of the parabola is kind of overpowering, to be honest, I guess the eggshells like thing. Maybe I'll do I didn't know how much to do this by. Let's say 0.1 y squared. So yeah, and then as you move along the y-axis, as the y coordinate changes, you'll see the z value being affected by having most of that look of a parabola going on. In fact, we can take out that wavy effect of the sine x plus sine y and just look at 0.1 times y squared. Now the x coordinate should have no influence on what z is, right? So it doesn't matter how much you increase the x value along the x-axis, you get this parabola. You get really a true parabola that has just been replicated over and over. Okay, so I hope use of that app was fun. By default, it's graphing sine of x plus sine of y plus 0.01 times the square of the sum of the absolute values of x and y. But you can type in a different function of two variables in the input box and see what that graph looks like, right? So this is a really neat app. It did not take me too long to design, but I hope you'll use it and see, just be creative, have fun, just see what you get, right? But like the picture is going to be three-dimensional because there's an x input and a y input, so those are your two input axes, and a z output. So here's the thing, we can also describe this same function by level sets. So for example, let's describe the inputs which have output 1, right? So again, the idea is you should first pick a specific output, like 1, and then we want to know when is the z coordinate going to be 1. So we just take this f of x comma y, or that would be z, plug in a 1 for that spot, and we're looking at 1 is equal to 2x plus y minus 4. Now you could give this to a student in college algebra, right? And if they rework it, I skipped the details, you would get y equals negative 2x plus 5. That's a line of slope negative 2 with y-intercept 5, right? And that's drawn in the xy plane. This level set, which is also more generally called a level curve, I like the term level set, but this is a two-dimensional object, right? There's an x coordinate and a y coordinate. I mean, this is drawn in the xy plane. Now let's go back. We'll go back to the function we've been looking at, 2x plus y minus 4, in a moment. For now, let's look at the following link. And I'd like to note that this link is going to take you to some function of two input variables. So the graph should be three-dimensional. What function? I did not show the formula for because it's just going to get a little distracting. There's some function, and its graph is shown here in purple. And what I've done here is I'd like to, without worrying about what specific function, just look at what level sets look like versus the graph of the function, right? So in purple over on the right half of the screen, you are seeing the graph of the function. It's kind of messy, whatever the formula for the function was. I just tried to type something that was going to create something interesting. So the z coordinate is letting you know the output, right? In the past, it was the y coordinate in y equals f of x. That would be the output. But here, x and y together are input, and then z is output. And so for the z of 3.5, that's what k equals here on the slider. So what we're trying to show is in this purple graph, which points have z coordinate 3.5. And so I've tried to get the computer here to draw in. Let me try to level this out a bit here. Yeah, if I level it out exactly, you're not going to see that red plane. So I'm just going to tilt it ever so slightly so you see the plane here. And where does this plane intersect the purple curve, right? Sorry, it's not a purple curve, it's a purple surface. This purple graph, where does this red plane of z equals 3.5 end up touching the graph in purple? And those, I'll try to do a little bit of a bird's eye view here. Those are depicted, let's see, I don't know if I've oriented this correctly. Let's do that. There we go. Because now I can see this green x-axis sticking out, towards the right. Let me try to rotate a little further. And oh, wait, what happened? Oh, the x-axis is in red here. Excuse me. Let me keep rotating. Now the x-axis is this way towards the right. The y-axis in green is pointing that way, and so it's oriented like this, and so the places of intersection are shown here, and that creates this shape. It really should be connected, but the computer is just struggling a little. Now if I change the specific output, like I do this and say, oh well, what combinations of x, y have lead to output 5.6, you're seeing those points here in red, and they're where this red plane intersects the purple, which is just so much data to take in, and it's hard to see in this 3D picture. Let's look over here at this 2D picture, right? All of the points along this curve, and then this funky like T-bone steak-like shape, and its copy in the second and third quadrants. Those points all together, all of these are XYs which lead to output 5.6. And then we could do things like this, z equals negative 0.3. What inputs lead to the output negative zero point 0.3. So for instance, I'm going to try to eyeball this, apologies, but it looks like there's a point right here where the x coordinate is 4 and the y coordinate is, well, roughly 5. So we're going to be a little off, 5-ish, right? But for x equals 4, y equals about 5. When you apply f, yeah, I mean, what I'm trying to say is f of 4 comma 5 should be negative zero point 0.3. And the statement's a little off, but I hope that works for you. And somewhere here, somewhere in this picture on the right, there's the plane z equals negative zero point 0.3 has been drawn for us. And where that red plane intersects this graph in purple, all of those points of intersection are shown in red on the left. Okay, so just for the sake of going through the slides, the slide here is trying to describe all of what we already saw, but this is just for the benefit of those who are not going through the video. But you will see two panels, right? So on the right is a graph of the function. The graph should pass the vertical line test. That is, any line drawn in the same direction as the blue z-axis should end up only going through the purple graph once. And in the left panel, there's a slider for which output you'd like to see the level set for. The level set corresponding to a specific value of k, it's shown two ways, right? So we saw that intersection of the red horizontal red plane. It's horizontal because it's z equals a number intersecting the purple curve. And on the left, we saw that drawing flat, right? It's just like which parts of this red plane are touching the purple. That's what's shown in red on the left. And you change the value of k to see a different level set.